Hello everyone, I'm Alka Jangid, TA for Nature and Properties of Materials. Today's lecture is Metals and Ceramics. Firstly, today's lecture is Metals and Ceramics, and this course is offered by Professor Vishak Bhattacharya from Department of Mechanical Engineering, IIT Kanpur. Firstly, we'll be going through some sample assignment questions. First question is the main form of ceramic degradation is, and your options are corrosion, weathering, dissolution, and swelling. So, your answer for this question will be weathering, because in case of weathering, it is a form of degradation. It is the main form of degradation of ceramics. It involves the breakdown of ceramics through contact with the Earth's atmosphere, water, and biological organisms. And while corrosion, it is prevalent in metals, while swelling is seen in mainly polymers. And swelling is phenomena where your solvent penetrates inside polymer, which leads to some change in volume. Now, second question is iron carbon alloy containing less than 0.83% carbon is called. Options are high speed steel, hypoeutectoid steel, hypereutectoid steel, and cast iron. So, answer for this should be hypoeutectoid steel, because in case of here when we see iron carbon diagram, we see that around 0.76 or 0.83 weight percent carbon. Below this, your steel will be hypoeutectoid steel, and above it, it will be hypereutectoid steel. And after 2.14, where we see eutectic reaction, your steel will, it won't be steel, it will be cast iron. So 0.8% is a eutectoid composition. So if carbon weight percent is lower than this, then it is hypoeutectoid steel, and if it is higher, then it is hypereutectoid steel. Now for the third question, the microstructure composition of perlite for a Fe3C diagram consists of, so it is asking perlite consists of what? So perlite, we know that perlite is a phase mixture. So it consists of, your options are carbon dissolved in iron having BCC structure, or carbon dissolved in gamma iron having FCC cubic structure, and a mixture of body centered iron and face centered gamma iron, or carbon dissolved in body centered iron and Fe3C. So we know that perlite is phase mixture of BCC iron and Fe3C. So answer will be T.
Madam,
Yes.
can you please share this questions to
Yeah.
my mail ID? Then it is very convenient to discuss.
What do you want me to share? Can you repeat, sir? Hello.
My mail ID is just I have typed in madam
Okay.
mail ID. Once again, I am typing my mail ID.
Okay. I think people from NPTEL, they will share these all material with you, like or the lecture recordings and this also. Otherwise, I'll
Madam, I have
mail you
typed in my
this
mail
also.
ID. Uh, if you share this, it is very convenient to discuss, madam.
Okay. So, in this question, answer will be carbon dissolved in BCC iron and Fe3C. So, in this, perlite is a result of eutectoid steel. So, at the eutectoid point, austenite transforms into perlite, which is a mixture of alpha iron, which is BCC structure, and cementite, which is Fe3C. So, So this reaction takes place in this manner. So your gamma, it will, when we'll be cooling it, it will convert into alpha iron, alpha ferrite, which will be 0.022 weight% carbon, and Fe3C, which is cementite, which will be having 6.7 weight% carbon. Now fourth question is perlite microstructure in an eutectoid steel consists of alternating layers of two phases, namely alpha ferrite and, so this is similar question. So perlite will also have cementite with it. Another layer will be cementite. So answer will be B. Now we can explain this by saying that perlite is a phase mixture of alpha iron, BCC structure, and cementite, Fe3C. So these phases exist in form of alternating layers. So this is your structure of perlite. So this is alpha and this is Fe3C. So these will be alternating layers in this structure. Can you mute yourself if you are not speaking? Okay, now question number 5th. It is vibration damping in machinery such as lathe is best achieved by means of base structure made of, and options are low carbon steel, ductile cast iron, grey cast iron, and white cast iron. So what should be the answer? Answer will be grey cast iron. Now we can describe it by saying that lathe beds are made using grey cast iron because of their high damping capacity and noise reduction, and its ability to create complex structures and cheap cost are the driving forces behind its popularity. So for grey cast iron, it is very easy to cast, and damping is one of the main factors to take into account. Vibrations that occur while using a lathe are brought on by noise, mechanical movements, or alternating currents. And damping, which is property of these cast irons, it dissipates energy, which lowers the vibrations. So mainly we use grey cast irons in making lathe beds. Now sixth question is which of the following is false about pilling bed width ratio? So your options are ratio greater than 2 indicates an unprotective layer, and second option is it provides this pilling bed width ratio, it provides indication about the protectiveness of oxide layer, or it is the ratio of volume of metal that is consumed in the oxidation to the volume of the oxide formed, or the ratio being less than 1 indicates tensile stresses in oxide film. So one of the statement is incorrect, and the rate it is this one, because the ratio is uh, volume of oxide formed divided by volume of metal that is consumed. So for good oxidation resistance, the oxide should be adherent to the surface. So this pilling bed width ratio, it is given as volume of oxide formed divided by volume of metal consumed in oxidation. So pilling bed width ratio, if it is lesser than 1, there will be tensile stresses in oxide film. So it will make it brittle oxide, it will crack and will become unprotective. And if it is in between 1 to 2, then there will be compressive stresses in oxide film, and it will be uniformly over a metal surface and making a protective layer. And if it is greater than 2, then it will be highly compressive stresses in oxide film, and this oxide will crack and flake off, and it will give an unprotective layer. Now question number 7. So any misinformation in the following rapid facts on steel alloys? The options are chromium improves oxidation and corrosion resistance, and sulfur decreases brittleness, and nickel increases hardness, and copper improves strength at high temperature. So answer will be B, because sulfur, we know that it, other statements are correct except sulfur decreases brittleness, because sulfur impurity, when it is present, it increases amount if it is in amounts higher than 0.05%. It causes brittleness because sulfur, it forms sulfide inclusions which sit at grain boundaries and it make steel brittle. Here at the this diagram also we can see that at the graph that mild steel, when it is higher in sulfur, it shows at even near room temperature it shows brittleness. Now, question number 8. An aluminium alloy has yield strength 145 megapascal. It has an average grain size of 2 micrometer and the Hall constant depicting resistance to dislocation is 70 MPa. So, if the grain size is reduced to 100 nanometer, what will be the new yield strength based on Hall page relationship? And your options are 226 MPa, 405 MPa, 105 MPa, and 358 MPa. So answer will be 405 MPa, and we can solve it by using this Hall page relationship. So we know that grain size, the grain diameter and the yield strength of material, they have a relation which is Hall page relationship. So sigma y is your yield strength. It is equal to sigma naught, which is a constant, plus ky, another constant, times d par minus half. So these are constants, they depend on material. And now, so first we'll be putting first values. So we'll be taking 70 MPa and we'll be putting diameter, grain diameter in micrometer, and this yield strength which is previously at 2 micrometer, and we'll be getting value of ky, and this value will be putting in the next equation when we'll be solving for this your sigma y at it is sigma y. So sigma y will be solving for 100 nanometer. So 100 nanometer will be converting it into micrometer, so it will be 0.1 and will be getting value 405 megapascal. Now question number 9. So the correct sequence of elements of 18 at stainless steel is, and your examples are, it is 18 at is chromium nickel, or it is nickel chromium, it is vanadium chromium, or chromium vanadium. So in case of stainless steel, this 18 at is usually chromium and nickel. So in 18 at stainless steel, 18% chromium is added to enhance corrosion resistance, and nickel is added 8% as an austenite stabilizer. So these act in synergy. So which one of the following cast irons consists of carbon in rosette form? Your options are white cast iron, grey cast iron, malleable cast iron, or nodular cast iron. Answer will be malleable cast iron. So in case of white cast iron, your carbon is in cementite network form. So it is shown here like in white cast iron, it will be in cementite form. And in case of grey cast iron, this is grey cast iron, here it will be in form of flakes. And in malleable cast iron, graphite is in irregular shaped aggregates, here it is shown, and this irregularly shaped aggregate, these are known as rosette. And in case of nodular or ductile cast iron, which is shown here, this graphite exists in spherical form. Now we'll be going through some lecture slides. So firstly, this lecture is metals and ceramics. So firstly we'll be going through metals. So metals, these can be classified into two main classes. First is ferrous metals, second is non-ferrous metals. So in case of ferrous metals, these will have base metal as iron, and in case of non-ferrous, so the metals or alloys that don't have base as iron. So ferrous can be further classified into steels and cast irons. In case of steel, they will have carbon less than 2.1 weight percent, and in cast iron, carbon percentage will be higher. In case of non-ferrous, these can be aluminium, titanium, copper, bronze, or other alloys of these metals or other metals. Now firstly iron. So the Iron Age, it began about 3000 years ago and it continues today. This carbon forms an interstitial solid solution when we add it to the iron. So it forms steel, as the atomic radius of the carbon is very smaller compared to atomic radius of iron. So the use of iron and steel, it has changed drastically the human development. So we use steel in a lot of things that we produce today. And iron, it possesses allotropy, which means it can exist in two or more different forms in the same physical state. So if temperature, for example, if temperature is below 770 degrees C, so it will exist as alpha iron, and this alpha iron will be ferromagnetic and it will have BCC crystal structure. If we increase this temperature above 770 and we go about up to 912 degrees C, it will be beta iron, which will be paramagnetic. So above 770, all all this iron will be paramagnetic in nature. So it will be having BCC crystal structure, and this crystal structure will change above 912 to up to 1394 degrees C. It will be FCC crystal structure. Then again it will turn into BCC crystal structure, which will be delta iron, and at this temperature it will melt, finally melt. So this BCC and this BCC are also different because these will have different lattice parameters. Now steel, it can also be classified into main two classes. It can be either low alloy steel or high alloy steel. Low alloy steel can be either low carbon steel, medium carbon steel or high carbon steel based on amount of carbon that is added. And high alloy steel, it can be tool steel, it can be stainless steel depending on alloying elements that are added. Now firstly low carbon steel, so it contains less than 0.25 weight percent, so also called mild steel. It is relatively soft and weak, and it has outstanding ductility about to 25% elongation. It has high toughness. It also has high machinability and weldability, and it is least expensive to produce, and it has tensile strength between 415 to 550 MPa. The applications for low carbon steel are that they can be made into beams, channels, nuts, bolts, wires, tin cans, etc. Now low alloy steel, these contain alloys such as copper, vanadium, nickel, molybdenum up to 10 weight percent. And if it is above 10 weight percent, then it will be high alloy steels. So these have high strength because presence of these alloying elements, and they also provide some corrosion resistance when compared to plain low carbon steels. These have tensile strength up to 700 megapascal. Now moving on to medium carbon steels. These contain carbon from 0.25 to 0.6 weight%, and these are stronger than low carbon steels but of low ductility and toughness. These have good wear resistance. And plain carbon steels which have a tensile strength up to 850 MPa, and alloy steel they have tensile strength up to 1900 MPa. So this difference comes from addition of alloying elements. And the applications of medium carbon steels are, these are used in making railway wheels, tracks, gears, crane shafts, etc. Now high carbon steels, these will have carbon from zero point 0.6 to 1.4 weight% carbon, and these are hardest, strongest and least ductile carbon steels. These can be alloyed with carbon and other metals to form very hard and wear resistant materials. For example, chromium, nickel, tungsten, molybdenum and vanadium. And the applications are in making cutting tools, because these should have very high hardness and wear resistance, and these are used in making dies, saws, concrete drills, etc. Now another steel is tool steel. It is commonly used in drill bits and other rotating cutting tools. So these are commonly used in drill bits and other rotating cutting tools, which are shown here. So it can withstand higher temperature without losing its hardness and toughness. So some alloying elements such as cobalt and tungsten, these are added in these for making them stable at higher temperatures. Now the example of tool steels are 1841 HSS, high speed steel. So it will have 18% of tungsten, 4% of chromium, 1% of vanadium, with a carbon content of 0.6 to 0.7%. So it is weight percent. This vanadium, it retains the smaller grain size. And cobalt high speed steel, it increases heat resistance. And molybdenum high speed steel, here molybdenum, it increases hardness and wear resistance, and it also a cost effective replacement for tungsten in tool steels. Now stainless steel, so as the name suggests, it is stainless, it doesn't rust. So it is highly resistant to corrosion in a variety of environments. So depending on environment which will be applying our steel to, so we add alloying elements according to that. So predominant alloy is chromium, which is at least 11 weight%. And example of 8 is 18 at stainless steel, in which 18% will be chromium and 8% will be nickel. And the applications of stainless steels are in making cryogenic vessels, food processing equipments, gas turbine parts, high temperature steam boilers, heat treating furnaces and nuclear power generating units. Now these are some alloying elements that are added in steels and their effects. So if we add boron for increasing hardenability without the loss of machinability, and chromium, it improves oxidation resistance and corrosion resistance, and corrosion resistance may also be enhanced by nickel and molybdenum additions. Cobalt and tungsten, it improves strength and hardness at elevated temperatures. Sulfur, we know that it increases brittleness, but it improves machinability when we combine it with manganese. Alone, it increases brittleness and lowers impact strength and ductility. Manganese, it improves hardenability and wear resistance, and it counteracts the brittleness caused by sulfur. Molybdenum, it improves hardenability and toughness, and it improves elevated temperature strength and creep resistance. Nickel increases strength and hardness without sacrificing ductility and toughness. Vanadium, it increases strength, hardness, wear resistance, and resistance to shock impact at high temperatures. Titanium, it improves strength and deoxidizes steels because it forms titanium oxide. So oxygen will be removed from steel. Now moving on to cast iron. So first and foremost is grey cast iron. In it, carbon content varies from 2.5 to 4 weight%. It also contains silicon, which increases the probability of forming of graphite flakes. So graphite exists in the form of flakes. Graphite flakes give self-lubricating properties and vibration damping capability. Strength and ductility are much higher under compressive loads, and it has tensile strength from 120 to 280 megapascal. Application, these are used in making base structures for machines such as lathe and heavy equipment that are exposed to vibrations. And white and or chilled cast iron, in these no graphite, carbon will be in form of carbide. So cementite is the hardest constituent of iron, so it is formed rapidly by cooling rapidly this molten iron. It is very hard, wear and corrosion resistant. It is almost non-machinable because of presence of cementite, and the application is in making rollers in rolling mills. This is the structure. Now malleable cast irons, these are formed by heating white cast iron. So in case of white cast iron, we saw that some it will be having cementite network. So we'll be heating it up to 800 to 900 degrees C for a prolonged time in a neutral atmosphere. It will prevent any oxidation and it will lead to decomposition of cementite. So cementite will break down into iron, ferrite and graphite. So this graphite will form in form of clusters. So this clusters are known as rosettes. So it is highly shock resistant and tough, and it has high tensile strength from 350 to 450 megapascal. It can be hammered to a small thickness, and the applications is in making connecting rods, transmission gears, pipe fittings and valve parts. Now other categories, ductile cast iron, which are also known as nodular or spheroidal cast iron. So these are obtained by adding some small amount of magnesium or other metals such as cerium to molten grey cast iron. So when we'll be adding it, these act as this nucleation sites, and making this leads to formation of graphite in form of spheres. So it has very high fluidity, toughness and wear resistance, and it has high strength up to 400 to 900 megapascal, and it has good machinability and weldability. Now effect of impurities on cast iron. So cast iron might have higher amount of silicon, so it will be providing formation of free graphite, makes iron soft and easily machinable. It also produces sound casting free from blowholes as having a high affinity for oxygen. So it will trap oxygen along with it, making silicon dioxide. And if there is sulfur, so it makes cast iron hard and brittle. Above 0.1% it makes unsound castings. Manganese, it takes care of sulfur. So when we add manganese, it makes cast iron hard by the formation of carbides, and it keeps control over harmful effect of sulfur. So when it will be forming manganese sulfide, it will be reducing amount of sulfur in form of other sulfides which can be harmful to cast iron. And phosphorus, it imparts fusibility and fluidity but induces brittleness. Now non-ferrous alloys, so these can be of two types. It can be either heavy alloys, can be either light alloys. So heavy alloys, it will have higher densities such as copper, nickel, cobalt, etc. in their alloys. And in case of light, it will be aluminium, zinc, titanium, etc. in their alloys. Now firstly, a very important metal is aluminium, which has crystal structure FCC. It has melting point, very low melting point, 660 degrees C. So it is very easy for production by melting and making some products. And it has density of 2.2700 kg per meter cube, which is light, and it has elastic modulus of 70 gigapascal. It has silvery gray luster, and it has very high thermal and electrical conductivity. So these are used in making electrical wires also, and in making these fins for cooling various these machinery and laptops and all these, they use aluminium. Titanium, now pure titanium, it has low density, 4500 kg per meter cube, and it has very high melting point, 1660 degrees C, and elastic modulus is 107 gigapascal. Tensile strength is between 150 to 500 MPa depending on some alloying or some strain hardening that is given to it. And its appearance is silvery grey white with metallic luster, and applications are it high strength and temperature components in biomedical and in making jewelry, etc. And alloying is required to reduce cost, so we avoid to make any component or part entirely with titanium to reduce cost, because it is very expensive and it increases strength can also be increased with alloying, and it controls phases. So as we know that in titanium there are two phases that are present. So below 883 degrees C, it will have alpha structure, which will be HCP, and beyond 883 it has beta structure, which is BCC. So there can be 4 titanium alloys possible. So it can be alpha, it can be near alpha, it can be alpha beta or beta depending on alloying element or percentage of alloying element. Now alpha phase stabilizers are aluminium, gallium, germanium, carbon, nitrogen, and beta phase stabilizers are molybdenum, vanadium, tantalum, niobium, manganese, iron, chromium, cobalt, nickel, copper, and silicon. So in making jet engine, these blades, rotor blades, these are all made by using titanium alloys. Now zinc, it has crystal structure HCP, and it has melting point of 420 degrees C, density of 7140 kg per meter cube, and it has silvery grey luster appearance, and it has very easy castability because of low melting point. Now, applications of zinc alloys. So, these can be used in making galvanic coatings on steel. So, because these will it will form it will oxidize earlier compared to steel, so it will provide some corrosion resistance to the steel underlying layer. And corrosion protection of structures by attaching as sacrificial anode, zinc carbon dry batteries, and dietary intake also, like zinc tablets are taken for fighting deficiency, which leads to weak immunity, slow brain growth, diarrhea, pneumonia, and it is found in spinach, cashew, seafood, cocoa beans, etc. Now, copper, it has crystal structure FCC and melting temperature is high, so which is uh, 1085 degrees C, and density is 8920 kg per meter cube. It is heavy metal, and it has distinctive reddish orange color, which is shown here, like a lot of these wires and tubes for heat exchangers. These are made using copper. These are these have good corrosion resistance because these are noble in nature. They don't make oxides that readily. And these are soft and malleable and ductile and very tough. These have good machinability, and these have high electrical and thermal conductivity. Now, thermal conductivity order is silver has highest thermal conductivity, then copper, and then aluminium. So, if we take 99.99% pure copper, it is used for wiring applications, and it possesses around 97% conductivity of silver at 1/8 of cost. Nickel. Now it has crystal structure FCC. It has melting point 1455 degrees C and density is 8900 kg per meter cube. It is also a heavy metal, and it has silvery white luster and a slight golden color. Now its applications are in making nickel metal hydride rechargeable batteries, in making monal metal. This monal metal is primarily composed of nickel and copper with traces of iron, manganese, silicon, and carbon. These have strong corrosion resistance, and heat exchanger tubes, food processing plant, marine application. These are some applications of monal metal. Now, super alloys of nickel and chromium based. So super alloys are what they are used at high temperatures. So high creep and oxidation resistant at elevated temperatures of approximately 1100 degrees C, and these are used in making turbine blades. Cobalt. Now it has HCP structure and density of 8900 kg per meter cube, and melting point is 1495 degrees C. It is lustrous silver gray metal, and elastic modulus is 209 GPa. Now its main application is production of high performance alloys. So it is mainly alloyed into steels and other alloys. So cobalt based alloys are also corrosion and wear resistant. And some high speed tools also contain cobalt for increased heat and wear resistance. These are also used in medical orthopedic implants, which is Vitalium, which is cobalt chromium molybdenum alloy, and it is alloyed with 95% of platinum for jewelry, and cobalt based blue pigment. It imparts a distinctive blue tint to glass, so it is also added into glasses. Now some strengthening mechanisms in metals. So the ability of a metal to plastically deform depends on the ability of dislocations to move. So thus restricting or hindering dislocation motion makes a material harder or stronger, harder and stronger. So some mechanisms to strengthen metals are as follows. So first is grain refining. So we'll be reducing size of grains. And second is solid solution strengthening. So in it we'll be adding some alloy elements. Other is strain hardening. So in it will be plastically deforming material. So it will lead to increase in number of dislocations which will interact with each other, making material hard. Now first process is grain refining. So a fine grained material, one that has small grains, is harder and stronger than a coarse grained due to a greater total grain boundary area to restrict dislocation motion. So sigma naught will be equal to sigma I plus ky upon root t. So sigma naught is yield strength, sigma I is frictional stress opposing motion of dislocation. It is a constant for a material, and ky is extent to which dislocations are piled up. So ky is also a constant, but it can vary with percentage of cold working that is provided. D is average grain size. Now the critical grain size, which is typically around 10 nanometer. So below this, if we reduce size of grains, the yield strength would either remain constant or it will start decreasing with decrease in grain size. And this phenomena is known as inverse Hall-Page relationship. Another method is solid solution strengthening. So pure metals are almost always softer than their alloys. Now if we add another element that goes into either interstitial or substitutional position in a solution, it increases strength. Now the impurity atoms, they cause lattice strain which can anchor dislocations. So the strain that is present in a lattice, it will hinder the motion of dislocations. So this is the reason why this pure metals are weaker while alloys are stronger. Now here it is shown like in copper nickel alloy. If we are increasing amount of nickel, tensile strength will keep on increasing and the ductility will decrease because these are inversely proportional. Now another method is strain hardening. It is enhancement of strength with increased plastic deformation. So strain hardening is the phenomena where a ductile metal becomes harder and stronger as it is plastically deformed. So it is called work hardening or cold working also, because the temperature at which deformation takes place is lower than melting temperature. And the effects of strain hardening may be removed by annealing, heat treatment. So if we anneal the steel or other metals, they will the strain hardening will reduce. So annealing is nothing but slow heating and slow cooling of material. Strength increases but ductility is sacrificed in this case when we strain harden a material. Precipitation or edge hardening. So this technique is used in very few alloy systems because it requires certain conditions in that particular alloy system. So this technique is used to increase yield strength of malleable materials like aluminium copper alloy, stainless steel and certain alloys. So based on changes in solid solubility with temperature to produce fine particles of an impurity phase, it blocks the movement of dislocation in a crystal's lattice. So alloys must be kept at elevated temperatures for hours to allow precipitation to take place, and this time delay is called aging. Now corrosion of metals. So one of the very important factor is spilling bed-worth ratio. So this is nothing but volume of oxide that is formed divided by volume of metal that is consumed in oxidation. So this is best metal and this is oxide layer that is formed. So we compare volumes of both of these. So if this, for good oxidation resistance, the oxide should be adherent to the surface. So if oxide is formed and it is adherent to the surface, so it will be a protective layer. So if this ratio, it is lesser than 1, then it will have tensile stresses in oxide layer. So it is lesser than 1, then it will be having a tensile stress, so it will be forming like this and it will won't be protective anymore because oxide is brittle. If it is between 1 and 2, which is in case of alumina, nickel oxide, copper oxide and chromium oxide, so in all these three we see that this ratio is between 1 to 2. So these have compressive stresses and it is uniformly over metal surface and it is a protective layer. And if this ratio is greater than 2, then it will have high compressive stresses in oxide film and these oxide will crack. It will be in this form and it will flake off and it will be unprotective in nature, which happens in case of iron oxide. In case of K2O, Na2O and MgO, in these there will be tensile type of stresses. So it also won't be protective. Now for the ceramics, this word is derived from the Greek term so ceramics word is derived from Greek term keramikos, which means burnt stuff. So burnt meaning something has oxidized. So clay is the earliest known ceramic which is used for making pottery, and ceramic materials are inorganic crystalline materials made from compounds of a metal and non-metal primarily held by ionic and covalent bonds. So glass by definition is not a ceramic because it is amorphous solid, but its mechanical properties, they behave similarly to ceramic materials because they have like high melting point and they provide refractory properties. So they behave similar to ceramic materials. Now some common characteristics are these ceramics are hard and brittle. For example, carbon in form of a diamond is the hardest known material. And these are strong in compression, typically 10 times the what they show in case of tensile, and these are weak in case of tension. And these are chemically inert because these are already in oxidized state. And these are insulators of heat and electricity except carbon in form of diamond and graphite. These are high and well defined melting points. These all have high melting points. Now classification of ceramics. So ceramics, these can be natural such as limestone. These can be abrasive such as ceramic carbide, tungsten carbide, L2O3 which is corundum, and silica sand. So these all have abrasive properties, and these can be refractories. Refractories meaning they can withstand very high temperatures, which are alumina, silica, bricks. pyre clay, zirconia, magnesia, beryllium oxide. These all are used in form of refractories. And glasses are non-crystalline silicates which contain other oxides such as calcium oxide, Na2O, K2O, and Al2O3, etc. Now, piezoelectric ceramics. These are barium titanate, lead titanate, lead zirconate titanate, PZT, and potassium niobate. These all act as piezoelectric materials, and these are used in making some sensors. Now, bonding in ceramics. So depending on type of bonding, ceramics can be classified into two types: ionic ceramics and covalent ceramics. So many ceramics, they exhibit a combination of ionic and covalent bonding types, the degree of the ionic character being dependent on the electronegativities of the atoms. So ionic ceramics, ionic bonding is predominant, so they are compounds of a metal with a non-metal, so these will have some electronegativity difference. So the electrostatic attraction between the unlike charges is responsible for dense packing. Examples are sodium chloride, magnesium oxide, zirconium oxide, aluminium oxide, etc. Covalent ceramics. Now, covalent bonding is predominant in these. They are compounds of two non-metals or occasionally pure elements. For example, graphite and other such as graphite and coal, all these consist of a single carbon atom. Bonds are formed by sharing electrons with their neighbors to give a fixed number of directional bonds. And examples are silica, graphite, diamond, etc. Now, failures in ceramics. So, ceramics have negligible plastic deformation before fractures. So, when ceramics they fail, they don't show any elongation before or plastic deformation before failing. So, they don't show any warning, such as metals when we see. So, there will be some ductile deformation, so we can know when a metal will fail. The brittle fracture of ceramics, they limit its application, so that's why we don't use these ceramics in many applications. Failure in ceramics occurs due to unavoidable presence of microscopic flaws, so micro cracks, internal pores, and atmospheric contaminant. So these all things can be present inside ceramics during fabrication. So when we are fabricating a ceramic, some cracks or pores, they can form inside it. Now the inherent flaws they lead to crack formation and propagation. So ceramics are good structural materials under compression, because if we are compressing a ceramic, then this crack they won't propagate, as it is difficult to crack to propagate, and the flaws they cannot closely control, cannot be closely controlled in manufacturing, which leads to a large variability in the fracture strength of ceramic materials. So this fracture strength, it depends on type of manufacturing that we have used or type of this reactants that we have used. So that's all from my side. So if you have any query, you can ask.
Madam,
Yes.
could you please send the numerical type questions which we have discussed in this session to my
Okay, this presentation I'll send you, okay? Is that fine?
Oh, okay,
Okay.
madam. Oh,
I've noted down your ID.
more
Okay.
than that, if any numerical type of questions are available with you, it is very helpful to me to solve the problems, or it will help to score more marks
Okay.
regarding this course. Any numerical type questions or any multiple uh, multiple answer type questions are available with you.
Okay.
Please, can you share?
Okay, I'll send you the initial 3 week that we have discussed. So presentation I'll share with you. I have noted your ID. Okay.
My mail ID is just I have typed, madam.
Yeah,
GPRKOR.
I've already noted. See, in chat you can see, right?
You have neatly presented, madam. Very nice presentation.
Okay.
Uh, Thank you very much, madam.
Okay,
Uh,
so if you have any query, you can ask, or yeah, that's it from my side. I'll be present here till 5 o'clock. You can leave if you want.
uh, Madam, uh,
Yes.
regarding number average molecular weight and equivalent mixture of the molecular weighted average molecular weight, those type of problems. Is there any problems?
Yeah,
Any questions regarding?
that assignment is still live, right? Its due date is not
That
over.
type of okay, that type of any numerical problems are with you,
Yeah, I
or a
will
degree of
be
polymerase.
sharing that in next week because that assignment is still live, I guess.
Okay, okay. I am asking that type of questions. Any other questions? That type of numerical problems.
Okay, in today's mainly whole page equation is there in today's lecture. Before that, and
What,
next
madam?
time we'll be having this molecular weight based, average molecular weight based questions.
Okay, 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 madam.
Yeah.
Today's presentation and questions. Could you please send me?
Okay, sure.
Today's presentation. Are you going to share, madam?
Yes, I will send you. Once the session is over, I'll send you.
Okay, thank you, madam. Thank you very much.
Okay.
I haven't received any mail, madam.
I'll send you after the session is over. Because I'm recording the screen, I
Okay,
can't
okay, okay,
write the mail right now, okay?
okay, 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 madam. Thank you, madam.
Okay.
Madam, are you going to end this session?
Yeah, you can leave if you want. I'll be present here till 5 o'clock. It's over. I think I've presented the slides.
Madam, small suggestion.
Yeah,
Madam, in the next lecture also, if you note down like this very important points and if you discuss some numerical problems, it will be more helpful to us, madam.
okay.
Thank you very much, madam. I am leaving this session, madam.
Okay, sure.
Oh, thank you, madam. Thank you very much. Please
Sure.
send, madam.
Sure.